I've come to every GopherCon so far. It just keeps getting better. Very happy to be here with all of you. I've had a lot of people come up to me and say they're really excited for my talk. I hope I can live up to those expectations. But I gotta say, what this talk is mainly about is what it would mean to add generics to Go, and why I think we should do it. It's not gonna be a razzle-dazzle talk. It's gonna be why, and then I'm gonna touch on how. A little bit of an update to a design we sent out last year for generics. So Go was released November 10th, 2009. Less than 24 hours later, we saw the first comment about generics. So we did add exceptions in the form of panic and recover, kind of a version of exceptions, in early 2010. So why generics? In 3 years of Go surveys, lack of generics has always been listed as one of the top 3 problems to fix in the language. What does it mean to add generics? And why should we want it? Generic programming enables the representation of functions and data structures in a generic form with types factored out. What does that mean? For a simple example, let's assume we want to reverse the elements in a slice. It's not something many programs need to do, but it's not all that unusual. Let's say it's a slice of int. Pretty simple. But even for a simple function like this, you'd want to write a few test cases. In fact, when I did, I found a bug. I'm sure many of you have spotted it already. We need to subtract 1 when we set the variable last. Now let's reverse a slice of string. If you compare reverse ints and reverse strings, you'll see the 2 functions are exactly the same, except for the type of the parameter. I don't think anybody here is surprised by that. What some people new to Go are surprised by is that there's no way to write a simple reverse function that works for a slice of any type. Most other languages do let you write that kind of function. In a dynamically typed language like Python or JavaScript, you can simply write the function without bothering to specify the element type. This doesn't work in Go because Go is statically typed and requires you to write down the exact type of the slice and the type of the slice elements. Most other statically typed languages like C++ or Java or Rust or Swift support generics to address exactly this kind of issue. So how do people write this kind of code in Go? In Go, you can write a single function that works for different slice types by using an interface type and defining a method on the slice type you want to pass in. That's how the standard library's sort.sort function works. In other words, interface types in Go are a form of generic programming. They let us capture the common aspects of different types and express them as methods. We can then write functions that use those interface types, and those functions will work for any type that implements those methods. But this approach falls short of what we want. With interfaces, you have to write the methods yourself. It's awkward to have to define a named type with a couple of methods just to reverse a slice. And the methods you write are exactly the same for each slice type. So in a sense, we've just moved and condensed the duplicate code. We haven't eliminated it. So although interfaces are a form of generics, they don't give us everything we want from generics. A different way of using interfaces for generics, which could get around the need to write the methods yourself, would be to have the language define methods for these kinds of types. That isn't something the language supports today, but for example, the language could define that every slice type has an index method that returns an element. But in order to use that method in practice, it would have to return an empty interface type, and then we lose the benefits of static typing. More subtly, there would be no way to define a generic function that takes 2 different slices with the same element type, or that takes a map of one element type and returns a slice of that same element type. Go is a statically typed language because that makes it easier to write large programs. We don't want to lose the benefits of static typing in order to gain the benefits of generics. Another approach would be to write a generic reverse function using the reflect package. But it's so awkward to write and slow to run that few people do that. That approach also requires explicit type assertions and has no static type checking. Or we could write a code generator that takes a type and generates a reverse function for slices of that type. There are several code generators out there that do just that. But this adds another step to every package that needs reverse. It complicates the build, because all the different copies have to be compiled, and fixing a bug in the master source requires regenerating all the instances, some of which may be in different projects entirely. All of these approaches are awkward enough that I think most people will have to reverse a slice in Go, just write the function for the specific slice type that they need. Then they'll need to write test cases for the function to make sure they didn't make a simple mistake like the one I made initially, and they'll need to run those tests routinely. However we do it, it means a lot of extra work, just for a function that looks exactly the same, except for the element type. It's not that it can't be done. It clearly can be done, and Go programmers are doing it. It's just that there ought to be a better way. For a statically typed language like Go, the better way is generics. What I said earlier is that generic programming enables the representation of functions and data structures in a generic form with types factored out. That's exactly what we want here. The first and most important thing we want to be able to do with generics in Go is to write the reverse function without caring about the element type of the slice. We want to factor out that element type. Then we can write the function once, write the tests once, put them in a Go-gettable package, call them whenever we want. Even better, since this is an open source world, someone else can write reverse once, and we can use their implementation. At this point, I should say that generics can mean a lot of different things. In this talk, what I mean by generics is what I just described, what the slide says. In particular, I don't mean templates as found in the C++ language, which support quite a bit more than what I've written here. I went through reverse in detail, but there are many other functions we could write generically. These examples are available in most other languages. In fact, I wrote this list by taking a look at the C++ standard template library. And there are also examples that are specific to Go with its strong support for concurrency. I've seen all of these functions written out many times with many different types. It's not hard to write them in Go, but it would be nice to be able to reuse an efficient and debugged implementation that works for any value type. And to be clear, these are just examples. There are many more general purpose functions that could be written more easily and safely using generics. And as I said earlier, it's not just functions, it's also data structures. Go has two general purpose generic data structures built into the language, slices and maps. We're all familiar with them. Slices and maps can hold values of any data type, with static type checking for values stored and retrieved. The values are stored as themselves. They're not stored as interface types. That is, when I have a slice of int, the slice holds ints directly, not ints converted to an interface type. Slices and maps are the most useful generic data structures, that's why they're in the language, but they're not the only ones. If we can write generic types, we can define new data structures like these that have the same type checking advantages as slices and maps. The compiler can statically type check the types of the values that they hold, and the values can be stored as themselves, not as interface types. And it should also be possible to take algorithms like the ones mentioned earlier and apply them to generic data structures. These examples should all be like reverse, generic functions and data structures written once in a package, reused whenever they're needed. They should work like slices and maps, in that they shouldn't store values of empty interface type, but should store specific types. And those types should be checked at compile time. So that's what Go can gain from generics. Generics can give us powerful building blocks to let us share code and build programs more easily. I hope I've explained why I think this is worth looking into. But generics do not come from the Big Rock Candy Mountain, the land where the sun shines every day over the lemonade springs. And by the way, for those who know the song, turns out Big Rock Candy Mountain's a real place. It's in Utah. The point is, every language change has a cost. There's no doubt that adding generics to Go will make the language more complicated. So as with any change to the language, we need to talk about maximizing the benefit and minimizing the cost. In Go, we've aimed to reduce complexity through independent orthogonal language features that can be combined freely. We reduce complexity by making the individual features simple. We maximize the benefit of the features by permitting their free combination. We want to do the same with generics. To make this more concrete, I'm going to list a few guidelines that we should follow. We should add as few new concepts to the language as possible. That means a minimum of new syntax and a minimum of new keywords and other names. As much as possible, the complexity of generics should fall on the programmer writing the generic package. We don't want the user of the package to have to worry about generics. That means it should be possible to call generic functions in a natural way, and it means that any errors in using a generic package should be reported in a way that is easy to understand and to fix. It should also be easy to debug calls into generic code. Similarly, we should make it easy to separate the concerns of the writer of the generic code and its user so they can develop their code independently. They shouldn't have to worry about what the other side is doing any more than the writer and caller of a normal function in different packages have to worry. That sounds kind of obvious, but it's not true of generics in every other programming language. Naturally, as much as possible, we want to keep the short build times and fast execution times that Go gives us today. Generics tends to introduce a trade-off between fast builds and fast execution. As much as possible, we want both. Most importantly, Go today is a simple language. Go programs are usually clear and easy to understand. A major part of our long process of exploring this space, and we've been exploring this space for more than 10 years, has been trying to understand how to add generics while preserving that clarity and simplicity. We need to find mechanisms that fit well into the existing language without turning it into something quite different. These guidelines should apply to any generics implementation in Go. So this is the most important message I want to leave you with today. Generics can bring a significant benefit to the language, but they're only worth doing if Go still feels like Go. Fortunately, I think it can be done. To finish up the talk, I'm going to shift from discussing why we want generics and what the requirements on them are to discuss the design for how we think we can add them to the language. At last year's GopherCon, Robert Griesemer and I published a design draft for adding generics to Go. Going through that design in detail is a different, longer talk that I'm not giving today, but I'll go over some of the main points. Here's the generic reverse function in that design. You notice the body of the function is exactly the same, only the signature has changed. The element type of the slice has been factored out. It's now named element and has become what we call a type parameter. Instead of being part of the type of the slice parameter, it's now a separate, additional type parameter. To call a function with a type parameter, in the general case, you pass a type argument, which is like any other argument, except it's a type. That's the int in parentheses you see after reverse. Fortunately, in most cases, including this one, the compiler can deduce the type argument from the types of the regular arguments, and you don't need to mention the type argument at all. Calling a generic function just looks like calling any other function, which is exactly what we want. Since Go is a statically typed language, we have to talk about the type of a type parameter. This meta type tells the compiler what sorts of type arguments are permitted when calling a generic function. And it also tells it what sorts of operations the generic function can do with values of the type parameter. The reverse function can work with slices of any type. The only thing it does with values of type element is assignment, which works with any type in Go. For this kind of generic function, which is a very common case, we don't need to say anything special about the type parameter. And indeed, we didn't. So let's take a look at a different function. Currently, both the bytes package and the strings package in the standard library have an index byte function. This function returns the index of B in the sequence S, which in this example can be either a string or a slice byte. We could use this simple generic function to replace the two functions in the bytes and strings package. In practice, we may not bother doing that, but it's a useful, simple example. Here, we need to know that the type parameter t acts like a string or slice byte. We can call len on it. We can index into it. We can compare the result of the index operation to a byte value. To let this compile, the type parameter t itself needs a type, a meta type. Because we sometimes need to describe multiple related types, and because this meta type describes a relationship between the implementation of the generic function and the callers of the generic function, we actually call the type of t a contract. Here the contract is named sequence. And as you can see, it appears after the list of type parameters. So in our current design, this is how the sequence contract is defined for this example. It's pretty simple since this is a simple example. The type parameter t can be either string or slice byte. Here, contract may be a new keyword or maybe a special identifier recognized in package scope. It doesn't matter for this talk. Anybody who remembers the design we presented last year at GopherCon will see that this way of writing a contract is a lot simpler. We got a lot of feedback on that earlier design that contracts were too complicated. We've tried to take that into account. The new contracts are much simpler to write and to read and to understand. They let you specify the underlying type of a type parameter and or list the methods of a type parameter. They also let you describe the relationship between different type parameters. We'll be publishing our updated design drafts with all the details soon, I think later today. Here's another example of a function that uses the string method to return a slice string of the string representation of all the elements in S. It's pretty simple. Walk through the slice, call the string method on each element, return a slice of the resulting strings. The code is quite readable, I hope. This function requires that the element type implement the string method, and the stringer contract, which we can see up there, ensures that. And here's the stringer contract. It simply says that T has to implement the method string returning a value of type string. You may notice that this contract looks like the funct.stringer interface. So it's worth pointing out that the argument of the toStrings function is not a slice of funct.stringer. It's a slice of some element type where the element type implements funct.stringer. The memory representation of a slice of the element type and a slice of funct.stringer are normally different. And Go does not support direct conversions between them. So this is worth writing, even though funct.stringer exists. This is an example of a contract with multiple type parameters. I know it's getting a little more complicated here. Here we're describing a graph built from nodes and edges, which are two different types in the contract. We're not going to require a particular data structure for the graph. Instead, we're saying that the node type has to have an edges method that returns the list of edges connected to the node. And the edge type has to have a nodes method that returns the two nodes that the edge connects. This is a busy slide, but it shows the signature of the function new that returns a graph, and it shows the signature of a shortest path method on graph. The important takeaway here is not all those details, but it's the fact that a contract isn't just about a single type. It can also describe the relationships between two or more types, in this case, the node type and the edge type. Now let's go to a little bit simpler. A surprisingly common complaint about Go is that it doesn't have a min function, or for that matter, a max function. That's because a useful min function should work for any ordered type, which means it has to be generic. While min is pretty trivial to write yourself, any useful generics implementation should let us add this function to the standard library. This is what it looks like with our design. The ordered contract says that the type T has to be an ordered type, which means it supports operators like less than, greater than, and so forth. And here's the ordered contract. This is just a list of all the ordered types defined by the language. The contract accepts any of the listed types or any named type whose underlying type is one of these types. Basically, any type you could use with the less than operator. There should be a comma after uint pointer there. It turns out it's much simpler to simply enumerate the types that support the less than operator than it is to invent a new notation that works for all operators. After all, in Go, only built-in types support operators. This same approach can be used for any operator, or more generally, to write a contract for any generic function intended to work with built-in types. It lets the writer of the generic function specify clearly the set of types the function is expected to be used with. And it also lets the caller of the generic function clearly see whether the function is applicable for the types that they are using. In practice, this contract would probably go into the standard library. And so really the min function, which would probably also be in the standard library somewhere, would look like this. There'd be a new standard library package contracts it would refer to the exported contract ordered defined in that package. Finally, let's look at a simple generic data structure, a binary tree. In this example, the tree has a comparison function, so there are no requirements in the element type. So I'm gonna show you this, but again, don't try to absorb all the details. It doesn't really matter. Here's how to create a new binary tree with the comparison function being passed in to the new function. This unexported method returns a pointer either to the slot holding V or to the unit in the location where it should go. Sorry about the formatting and the type size. I got a bit squeezed for space. Anyhow, as I say, the details don't really matter, especially since I haven't actually tested this code. I'm just trying to show what it looks like to write a simple generic data structure, and I hope what you can see is that it looks like writing Go. Here's the code that tests whether the tree contains a value. Here's the code for inserting a new value. You'll notice here there's a type argument, E, to the type node, down on the second to last line of code there. Again, the details don't matter. The point is to show what it's like to write a generic data structure. As you can see, it looks like writing ordinary Go code, except that some type arguments are sprinkled in here and there. Actually, using the tree is pretty simple, and that's how it should be. It's a bit harder to write a generic data structure because you often have to explicitly write out type arguments for supporting types. But as much as possible, using a generic data structure is no different from using an ordinary, non-generic data structure. That's the last example I'll show. As I mentioned, we'll soon publish an updated design draft that explains how all this code is intended to work. We're also working on actual implementations to allow us to experiment with this design. It's important to be able to try out the design in practice, to make sure we can write the kinds of programs we want to write, examples like the ones I showed earlier in the talk, and many more. Implementing this hasn't gone as fast as we'd hoped, but we'll send out more details on these implementations as they become available. This CL will be for modifications to the Go types package to permit testing whether code using generics and contracts can actually type check. It's incomplete right now, but it mostly works for a single package, and we'll keep working on it. What we'd like people to do with this and future implementations is to try writing and using generic code, see what happens. We want to make sure that people can write the code they need and that they can use it as expected. Of course, not everything's going to work at first, and as we explore this space, we may have to, I'm sure we will have to, change things. And to be clear, we're more interested in feedback on the semantics than on details of the syntax. So, I'd like to thank everyone who commented on the earlier design and everyone who's discussed what generics can look like in Go. We've read all the comments. There have been a lot, but we've read them. And we greatly appreciate the work that people have put into this. We would not be here today without that work. Our goal is to arrive at a design that makes it possible to write the kinds of generic code I've discussed today without making the language too complex to use and without making it not feel like Go anymore. We hope this design is a step toward that goal, and we expect to continue to adjust it as we learn from our experiences and yours what works and what doesn't. If we do reach that goal, then we'll have something we can propose for future versions of Go. Thank you.